Today we're going to be looking at an interesting little algorithm called Floyd-Steinberg Dithering, and using it to improve the quality of images made by my printer bot. To illustrate the difference in quality, this is what this video would look like if it was being displayed in Minecraft using blocks with the old method. And this is what it looks like when we apply Floyd-Steinberg Dithering. Making a bot print an image in Minecraft is actually pretty simple when you break it down. We have a list of blocks and a colour for each of them. The colour can either be the average colour of the block or the dominant colour. This list of blocks is called the palette, and it can be a list of all the blocks or just a subset like wool or concrete blocks. When we want the bot to print an image, it loops through each pixel, finds the block with the closest matching colour, and places down the block that corresponds to that colour. It's pretty simple, and probably a good project for anyone learning to make their own Minecraft bots. That being said, there is a bit of a problem with this approach. There are a lot less colours of blocks in Minecraft than there are possible colours in an image, so our bot inherently has less colours it can work with when trying to produce an image. This leads to a few different problems. The most obvious is probably inaccurate colours, but there are a few things like subtle gradients being reduced to a single block, and not so subtle gradients being reduced to a series of thick bands. All of this adds together to get a picture quality that, while not bad, isn't great. The solution to this is called dithering, which is where we use a combination of blocks to create the effect of having more colours. For example, if we have light blue wool and white wool, we can tile them like this to make an even lighter blue. And we can use different patterns to produce even more shades. Or if we have a gradient from red to blue, we can use dithering to break up the colours a bit. And this can look good even if we only have a couple of blocks to work with. You might think this would be kind of difficult or complicated, but it's really not. As I've already mentioned, the specific dithering algorithm I'm using is called Floyd-Steinberg Dithering. It's surprisingly straightforward once you wrap your head around it. Just to be clear, I'll only be showing snippets of code in this video to illustrate how it works. All the code for the bot is available on GitHub through the link in the description. Let's start by going through how to do this using only two types of blocks to build grayscale images, and then modifying that code to work in colour with any block. I'm using the getPixels module to get the RGB values from the image and storing them in a sort of 2D array. This is also how I control the scale of the images in the Minecraft world. The first thing to do is to convert our image into grayscale, which involves taking the RGB values and converting them into a single value called luminance, which represents how bright the pixel should be. The simplest way to do this is averaging RGB values, but each value contributes different to the perceived brightness of the original image, so it's better to weight the values by different amounts. According to a quick Google search I just did, these are the magic numbers we need. If we try running this on a few images, we get these new grayscale images. Let's try building these images. We just need to loop through all the pixels and place the blocks. To get the correct block, we're just checking if the luminance of the pixel is above a certain threshold. White concrete if it is, and black concrete if it's not. In mineflayer, you can place blocks with the placeBlock method, which mimics the way a normal player places blocks. But it can be slow and a little bit hard to work with for larger scale projects. So to make things easier, we can use commands. And these are our results in-game. Bob Ross kind of looks like he's trying to sell me fried chicken, but it's nothing a little bit of dithering can't fix. We'll start by looping through all the pixels and getting how bright this pixel is supposed to be. Then we want to get how bright the pixel will actually end up being in the world. In our case, the block could either be black or white, and we're just getting which of these is closer to our target luminance. And here's where we get to the meat of Floyd-Steinberg Dithering. We want to first calculate what's called the error, which is a measure of how different our target luminance is to the actual luminance. This represents how bright we want the pixel to be, and this represents how bright the actual block will be. And the result is a measure of how different they are. As an example, let's say you have a target luminance of 200. It would end up getting rounded up to 255, or just white. Our error in this case would be -55, because the luminance we wanted is 55 lower than what we actually got. But in some cases we would be rounding down, so the actual luminance would be lower than what we wanted. And in these cases the error would be a positive number. The idea is that we want to distribute this error to the surrounding pixels of the image, so that if our pixel ends up being brighter than we wanted, we make the surrounding pixels darker to compensate. Or conversely, if our pixel is darker than we wanted, we make the surrounding pixels brighter. In terms of the actual numbers, we don't actually change each of the surrounding pixels by the same amount. You might expect that if we have an error of 24, since there are 8 neighbours, we would increase each of them by 3. But we can also use what's called a distribution pattern, which describes how much of the error affects each of the neighbours. In Floyd-Steinberg dithering, the distribution pattern looks like this, which means we add this fraction of the error to the corresponding neighbouring pixels. There are a couple of things to note about this distribution pattern. First, you'll notice that only the pixels down and to the right are actually being affected. And second, these fractions add up to 16, or 1 whole, so that the total amount of brightness in the image stays the same when we distribute the error. These aren't things you need to worry about, it's just a couple of interesting things to take note of. Implementing this in code is very easy, since we're just adding numbers. But not if we're on the edge of the image, because that doesn't make a whole lot of sense. And now that we've finished dithering, we can do one more loop through the pixels and place down blocks based on the luminance just like before. I think the images look a lot better at higher resolutions. But if we have higher resolution images, dithering takes longer, which can be a little annoying because our bot needs to finish doing that before it starts building the image. We can actually kind of remedy this by removing these loops and moving the code for placing the block in this loop here. This works because the error distribution pattern for Floyd-Steinberg dithering only spreads the error down and to the right. So if we're looping through pixels from top to bottom and from left to right, we know that the pixels we haven't dithered yet can't affect the brightness of the ones we've already computed. The next step in our journey is to make the bot dither coloured images, which is actually very straightforward. We just need to make a few small changes to the code. Instead of converting the image to grayscale, we'll keep each of our colour channels. Then, when we are dithering, our target luminance becomes separate target RG and B values. We'll then need to replace this code for getting the real luminance of the block by first getting the block that best fits these RGB values, and then using that block's average colour for our separate real RGB values. We'll calculate separate errors for each of these RGB values and propagate them all accordingly. Kind of like we're dithering 3 separate grayscale images simultaneously. And now we just need to place the block, which we already have from earlier. The result is images that I think look a lot nicer. But maybe you disagree. I'll see you guys in a few weeks with my next video. Feel free to leave your ideas, suggestions, feedback or whatever in a comment. Consider giving this video a like and subscribe if you haven't already.